Today's presentation is about cosmological constant, an experimentalist approach. The overall idea of this approach is all physical laws are merely approximations, fits, to be replaced by beta fits in the future. Now, what's the problem with cosmological constant? There are two of them. One is extremely large, one is normal, gravitational type. In order to understand this contradiction, it's necessary to come back to Einstein's time. At Einstein's time, only two forces were present. In general relativity, gravity was changed to space-time curvature, so the cosmological constant for static universe would be this value, and that would correspond to 2.32 times 10 to the power of minus 52 meters to the power of minus 2 for stationary universe. Next comes the great Einstein's blunder, who decided to get rid of stationary universe, delete this cosmological constant, so the solution of equations are now non-stationary, and that was a concept of Big Bang, which is still present today. What happens in the future? In 30s, 40s, 50s, two more forces were discovered. The idea of quantum vacuum appeared, and it turned out that the quantum vacuum has enormous energy, and it should be another new cosmological constant, 10 to the power of 120 times lambda. Very, very big one. Which one is correct? The answer is both are correct. Let's consider more accurately those universes. Which first fit of our universe would be Einstein universe. No quantum vacuum is present. Vacuum is absolutely really empty. What it means? It means that speed of light is exactly c, and it is postulated. No influence of quantum vacuum, like Kerr effect in quantum vacuum, is possible. No Casimir effect is possible. G factor of electron must be exactly 2, no deviation. No difference between G factor of electron and muon. Spontaneous decay of atom is somehow appears inside atom itself, and not understandable why it decays. And in addition to gravity, which is now curvature of space-time, only electromagnetism is present, governed by Maxwell equations. The presence of something else is strongly forbidden, and here comes the philosophical idea that it doesn't any matter how big is something, if it is not influencing your universe at all, just zero, then it means it does not exist. So you can imagine everything as big as you want. If the interaction between your universe and that something is zero, it can be present or not present. For physics, from physics point of view, it is non-existing. And the fit of all this would be the approximation, the fit of this universe would be general relativity with lambda equal to this value. However, discoveries were made, and now we all know that quantum vacuum is real. It is something, it's called quantum vacuum. In science fiction, it's called subspace. Something is present. What effects are responsible? First of all, simultaneous decay of excited state is caused by quantum vacuum fluctuations. Atom decays from excited state and emits photon. Nucleus decays from excited states, emits gamma quant or something else, just decays. And it is found that this effect is present even in complete vacuum, no influence from other atoms, from media. Why it's present? Quantum vacuum. Quantum vacuum is present and causes the effect. Speed of light is now not absolute. The quantum vacuum Kerr effect is postulated and discussed. The effect is very small, enormously small, but present. G factor of electron is now 2.0029, is not equal to 2.0. Quantum vacuum fluctuations, influence of quantum vacuum is present. Casimir effect discovered, Delbrück effect discovered. G factor of electron is not equal to G factor of muon. They are different particles, and G factors influence differently by quantum vacuum. Electron-positron pairs generation by quantum vacuum if the electric field is strong enough, etc., etc. And conclusion, quantum vacuum is real. And therefore, new cosmological constant for the whole universe would be 10 to the power 120 times lambda plus lambda. This small lambda is because Einstein's universe is obviously present. How to reconcile both universes? The easiest idea, speculative idea, would be to imagine, for example, a bunch of hockey pucks on a skating rink. Suppose energy conservation law, no losses at strikes. Friction at ice is absolute zero. What would be this bunch of pucks behave? They would just strike and scat around, just strike and scat and strike and scat forever. That would be some kind of model of Einstein's universe. However, nothing is real, absolutely real. Nothing is zero. Nothing is absolutely zero. And one day, inhabitants of this universe would discover that some friction exists, and for some unknown reasons, the pucks are breaking more than they should be. They're interacting somehow with something, and they would discover kind of quantum vacuum. They would investigate what's this, and they found that there is an ice under the universe, and ice is enormously thick, has enormous energy, and it means that the real universe now, not only those hockey pucks, but the ice underneath together will generate an enormous cosmological constant for this universe. And the situation is our universe is similar. So we have kind of total universe can be considered as sum of major quantum vacuum universe, all other forces in addition to gravity and electromagnetism, and quantum vacuum that generates an enormous, very big cosmological constant. And our household universe, you may call it Einstein universe, only electromagnetism is present, no quantum vacuum. But since the quantum vacuum is influencing, but only weakly, we must consider both of it. So total universe will generate, will unify both cosmological constant into one. So the idea is that different fits of the same universe will lead to different cosmological constant. No contradiction here, because any theory is only a fit, nothing more. Now, most interesting question. Is it applicable to Big Bang? Can we insert Big Bang into those universes? Suppose energy conservation law is valid, and now Big Bang is present. What it means? It means it creates space-time. Space-time, because of quantum vacuum, has an enormous energy inside. It means that somehow Big Bang is constantly creating new energy, new space-time. And this is impossible because Big Bang is over, all energy is already exposed. In reality, it means even more energy every time is created and created because universe is expanding. This is completely impossible. Can Big Bang, however, be saved by the idea that interaction is enormously weak? So it's kind of, we have quantum vacuum universe and our Einstein universe simply expanding inside. If it is expanding, it can be a Big Bang, then it's simply expanding. Friction is not zero, quantum vacuum is present, but very low. So Big Bang exists, and then it's simply expansion. Again, it is contradiction here in a sense that since quantum vacuum is exchanging energy with Einstein universe, and Einstein universe supposedly expanding, the quantum vacuum energy will be stochastically. It's back in all directions, but energy from Einstein's universe toward quantum vacuum will be in the same direction because it's expanding. That creates kind of drag. So it means that the accelerating or simply moving stuff, exchanging energy with stationary stuff, and that creates a drag. Friction, kind of friction. It means such Big Bang should be quickly breaking, so any expansion is breaking, and the more expansion, the stronger the breaking force. For example, the idea of accelerated expansion, like from supernovas, is completely impossible. It should be accelerated breaking. And even very weak expansion, very weak interaction must lead to, in cosmological times, to quick loss all the energy of Big Bang and generation of stationary universe. So that again means that Big Bang is very unlikely. Most probably it is stationary universe, and something local event like extremely strong explosion of supernova will be breaking in questions of millions of times, definitely not trillions like should be for static universe.